attention to this chapter so that you get to know how to explain all, how to understand all this. Okay, okay. So without any session, let's begin. Okay, so we are going to enter to the final subtopic for chapter 6, which is 6C, phase equilibria. Okay, so what are we going to learn in this chapter? So we are basically going to learn about phase equilibria, about mixture of two liquid, mixture of two liquid. Okay, so actually previously we have already learned in chapter 4.2 about vapor pressure. So what is a vapor pressure? So a vapor pressure is exerted when a vapor is colliding with the wall of a container. Okay, so let's say if now you have two individual liquid, namely liquid A and also liquid B. So it is measured that the liquid A will vaporize to give vapor A. Liquid B will vaporize to give vapor B. So their vapor pressure measured at room temperature pressure are 100 kilopascal and 150 kilopascal respectively. So in other words, in here, we say that B has a higher vapor pressure than A. So in other words, we say that B vaporize easier compared to A. Now, this is something that you must be able to identify and tells based on the vapor pressure, which one is easier to evaporate, or in another word, which one is easier to become gas. Because the principle of applications for phase equilibria is based on the equilibrium between liquid and gas later. Now you shall see what am I going to mean based on what I've already mentioned just now. Which one is easier to become gas? So now, what is basically ideal solution is all about is when now you are mixing the two liquids together. Okay, so when you are mixing liquid A and liquid B, there may be three possibilities. So what are the three possibilities we are talking about? Number one, we have what we so-called as a miscible solution. Okay, miscible liquids or miscible solutions. So a miscible solution is formed when two solutions can dissolve completely with each other and form a homogeneous solution. So for example, when you try to dissolve ethanol and water, okay? Then you have what we so-called as an immiscible liquid. So immiscible liquid forms two separate layers of the solution when you mix two solutions together. Okay, so it's like water and oil. So if you mix together water and oil or water with benzene, you eventually see two layers, isn't it? So we call that liquid as immiscible liquid. And then there are also what we so-called as a partially miscible liquid. So when two solutions are mixed, only a little amount of solution can mix with each other, but there are still two very visible layers observed in between each other, okay? But in this case, we are mostly going to discuss about this one, which is miscible liquid. So we use the terms miscible to explain how does two solutions mix together, okay? Not soluble. Soluble is between solid and liquid. We use the term miscible for two liquids, okay? Okay, so now, what are the applications that we can use in order to explain how miscible is two liquids and what will happen in between them? We use what we so-called as Raoult's law, okay? We use Raoult's law in here. So Raoult's law suggested that if two solutions are ideals when mixed, you shall have these three postulates occur. What are the three postulates? Number one, intermolecular forces between A is the same with the intermolecular forces of B. And what happened after you mix A and B together, their intermolecular forces is also almost the same. Number two, when this happens, there shall be no changes of volume when solutions are mixed together. What does it mean by this? It means that when you mix A 50 centimeter cube, B 50 centimeter cube, so total volume of the solution will be 100 centimeter cube exactly. Okay, this is number two. And then number three, no enthalpy change of the mixing solution. So in another word, there shall be no heat absorbed or released when you mix these two solutions together. Okay, so this is what the three postulates of the applications for Raoult's law. Okay. Okay, so now we are going to see how does we apply Raoult's law in between two miscible liquids. So Raoult's law, which states that the vapor pressure of a solution, okay, the vapor pressure of a solution, okay, I highlighted it. Raoult's law says that the vapor pressure of a solvent or solution PA is given by the vapor pressure of the pure solvent A, okay, PA naught. The terms PA naught in here means the pure vapor pressure of the solution. Multiply with the mole fractions of the mixture, okay? So, because when you mix A and B, you mix at a certain portion. So this certain portion can eventually be fractionalized. That means you can use it as a fraction. And this fraction is only doable in terms of mole. Okay, so you must always use back the mole concept to calculate the mole fractions in here. So therefore, in an ideal solution, the vapor pressure exerted in the substance A is the mixture of solution AB is dependent with the total amount of mole of A and the vapor pressure of the pure A itself. So this formula is the first formula that you would like to remember for today. So let's together have a look at the examples of calculations for Raoult's law. Okay, so when 1 mole of A and 1 mole of B are mixed together in equal volume, vapor pressure exerted by each A and B can be calculated by using Raoult's law. So how do you apply it? So vapor pressure in the A of the mixture is equals to PA equals to XA times PA naught. Okay, this is multiplier. The black dot in here is multiplier. So you substitute. So PA equals to 1.0, which is the mole of A, divided by the total mole, 1.0 plus 1.0, multiplied by the pure vapor pressure of A, which is 100 just now. Press your calculator, you should get your PA equals to 50 kilopascal. Whereas the vapor pressure of B in the mixture is, vapor pressure of B is equals to mole fraction of B multiplied by the pure vapor pressure of B. Substitute inside your equation. So PB equals to 1.0 divided by 1.0 plus 1.0 multiplied by the pure vapor pressure of the B, which is 150 kilopascal. As a result, you get pure vapor pressure of B, not A, B, sorry, typing error. PB equals to 75 kilopascal. So vapor A, liquid A, exerted pressure of A at 50 kilopascal. Mixture of liquid B exerted vapor pressure B at a total of 75 kilopascal also. So the total vapor pressure is the vapor pressure of A summed by vapor pressure of B. This one, because now you are in vapor, you are in gas. When you are in gas, you can no longer use Raoult's law. You have to apply Dalton's law partial pressure. So if you still remember what is Dalton's law partial pressure, Dalton's law partial pressure stated that total vapor pressure of the mixture in a mixture is equal to the summation of the partial pressure exerted by each individual gas. So as we described just now, vapor pressure A is 50 kilopascal, vapor pressure B is 75 kilopascal. So the total vapor pressure in here is 125 kilopascal. So in short, we say that now this is a mixture between two equilibrium in here. I mean, two different law applications in here. So what does it mean in here? Wait, I'm going to help you to understand better. Okay. Okay, so what does it mean in here? So now you have a vapor pressure of A mixed with vapor pressure of B in here, isn't it? Okay, so now they are mixed together inside a pure vapor pressure of A and B in here. Can you give me like 2 minutes? I draw out the figure for you so that you can see together. So now after you're mixing in between the two liquid, you mix together, what will you get? Give me the time. I try to find the clip where it is. Okay. Okay, now when you mix these two together in between here, okay. So you now shall have a mixture in between liquid A and liquid B. So I uses different color lah, so that you can see clearly what is the difference in here lah. Okay, okay. So now in this case, you shall have two different laws that you would like to apply in here. So for the liquid contain, okay, for the liquid contain, you are going to use what we so call as Raoult's law, where you use PA, okay, is equals to, let's wait, XA time PA naught. Okay, whereas in here, you shall have PB. Okay, you calculate for two different individual PA and PB, is equals to XB times PB naught in here. Okay, so in the liquid phase, you are going to apply Raoult's law. So now, eventually, all of them will be vaporized to become vapor A and vapor B, isn't it? Okay. Wait, oh, I didn't share screen. Okay, sorry. You all didn't see this screen, right? Okay, so you see here, inside this mixture, you have liquid A and liquid B working in here. Okay, so now each of these individual liquid A and liquid B vaporize to give vapor A and vapor B individually. Okay, now don't forget because now B can vaporize more, isn't it? So when B can vaporize more, you shall expect more vapor B, which is in blue dot, compared to vapor A. Why? Because even under equal mole, since B has a higher vapor pressure, that means B is easier to vaporize compared to A. So as a result in here, what will happen is, so in between the two mixture in here, okay, you shall have more vapor B compared to vapor A. Why? As I explained just now, it is because B is easier to vaporize compared to A. Therefore, you shall have more vapor B compared to vapor A, even though their mole is the same. Okay, so that is what we mean in here. Okay, so now they have become vapor. So once they have become vapor, you are going to use Dalton's law partial pressure, where Dalton's law in here says that P total is equals to PA plus PB. Can you all see the screen right now in here? In here?
Yes.
Yes, okay, good. Okay, so this is the part where you use Raoult's law, and this is the part where you use Dalton's law. So now, because both of the liquid mixture has already been vaporized, isn't it? Now you shall have gas A and gas B mixed together. So even though you have the same mole of A and B in the example just now, does it mean that the vapor of A has the same mole with vapor of B? It is going to be totally different, because if you remember of what I've mentioned just now, I say that when vapor B has a higher vapor pressure, That means it vaporizes easier. When you vaporize easier, in terms of vapor, you are going to have more B compared to A. Now, if the most direct way that I explain here is you see more blue dot has 6 dots compared to red dot has 5 dots in here. So what does this significantly changes? This will also significantly changes the mole fractions inside the vapor content. So how to calculate the mole fraction of the vapor content in here? So you can calculate also by using, because now it's in gaseous state, isn't it? So mole fraction in gaseous state, you can use Dalton's law. Okay, you use Dalton's law to explain the mole fraction in gaseous states in here. Okay, so what is the mole fraction? How to calculate mole fraction in Dalton's law? If you still remember, we say that XA is equals to, XA is in terms of gas. I use a capital letter so that you can see the differences. Okay, is equals to what? Do you still remember? PA over P total. So generally, these are the 3 equations that you are going to apply later in order to calculate the mole fraction of A and mole fraction of B. So now, this is the mole fractions of A in here. Now, how to calculate mole fraction of gas B? There are 2 ways. Either you use this same formula, or you can use what? Because a mole fraction, at the end, the summation is what? Is equals to 1, isn't it? So once you have already calculated for A, you can also use the mole fraction to calculate 1 minus XA. So you can use this law to explain here. Okay. Let me see. Sorry, this is a little bit messy here. Okay, so generally, these are the 3 basic steps that you have to know to calculate the vapor pressure of pure A and also pure B in here. Okay, let's go back to the slide. Okay. So these are the 3 very important equations that you have to remember by heart on how to calculate the vapor pressure of A and B accordingly. Okay. So starting from the first equation, where the first equation in here, you use Raoult's law to calculate PA and XA, PA and PB respectively. So PA and PB is in the liquid mixture. So after you get the vapor pressure of A and vapor pressure of B, then you continue with step 2 using Dalton's law to calculate the total pressure. So the total pressure in here is PA plus PB. So now, it doesn't mean that when liquid you have the same mole fraction. In gas, you can also have the same mole fraction. No, they are totally different because they have different vapor pressure. So to calculate the mole fractions, you have to use the Dalton's law application, where you can use mole fraction in terms of gas. We are talking about in terms of gas. Is equals to PA over P total, while gas B is equals to PB over P total, or you simply 1 minus XA, because the total mole will be 1, total mole fraction will be 1 mole. So I hope that you can understand on how to apply these 3 simple equations in the Dalton's law, in the Raoult's law in here. Okay. Okay. So now we shall have a look at the examples of how to calculate the vapor pressure of A and B and how to get the mole fraction of A and B accordingly. Okay. Okay. So now, after these 3 laws that we apply, we are going to apply for a series of the different mixture of A and B at different mole fraction. So this table is trying to tell you what is the mole fractions for different mixture of A and B. So we start from here. The first one says that mole fraction of A equals to 0 and mole fraction of B is equals to 1. So this is the comparisons in here. It's either A and B. In here, we say that when mole fraction of A is 0 and mole fraction of B is 1, it means that now the whole mixture contains only B. So that's why this is indicating for XB equals to 1, this will be equals, this is indicating what? This is indicating the pure vapor pressure of B. Okay, so this is the pure vapor pressure of B in here. So the pure vapor pressure of B in here is 150 kilopascal. So total pressure of A and B is 150 lah. So we use different mole fraction to calculate. Okay, so if A 0.05, then B must be 0.95. So you calculate the vapor pressure, A 5 kilopascal, B 142.5 kilopascal, total pressure 147. Then you have mole fraction of A 0.1, mole fraction of B 0.9, vapor pressure of A and B are 10 and 135 kilopascal respectively. So you calculate all the way through the end. Okay. So at the end, you shall have pure vapor pressure of A equals to 1, which is 100 kilopascal. And then pure vapor of B is 0. So this is vapor pressure of B. So in here, so you can see that in here, there is no vapor pressure of B, isn't it? So in another word, here is the pure vapor pressure of B. Sorry, A. Here. Okay. So this is what happens after the calculations. So now, what are we going to do? We are going to move this data, okay, pressure exerted by A, pressure exerted by B, total pressure in a graph form. So what will happen if you move it to the graph? So the graph will look more or less like this. Okay, so what are this line actually represent? This line actually represent, number one, this is the total pressure of the mixture, where you have P total equals to PA plus PB. Okay, where the blue line in here indicates that vapor pressure of A, vapor pressure of B. Okay, where this red line represents vapor pressure of A in the mixture in here. Okay, so whereas this one, okay, indicate the pure B, and this will indicate the pure A in here. Can you understand? Okay, so this is what this graph is all about. So now, this graph is generated based on the formula based on the data that we have seen just now, okay? Where the data in here, as you can see, okay? These are the informations that we transfer into here, okay? Okay, so this is only the beginning where we are going to learn how to apply Raoult's law and also Dalton's law. So up until here, we are only actually at step 1 and also step 2 only. We haven't finished step 3. So step 3 is calculating mole fractions of gaseous mixture. Mole fraction of gaseous mixture. So how are you going to apply mole fractions of gaseous mixture? We are going to apply the formula that we learned just now, the third one, where XA is equals to PA over P total, while XB is equals to PB over P total in here. So after recalculate the vapor pressure of A and B accordingly, I'm so sorry here. I might make a little mistake in terms of, oh, no, okay, sorry. We continue. Okay, so now, just now, we have total vapor pressure at 0.5, 0.5, isn't it? So at 0.5, 0.5, okay, I'm following this one, sorry, because my slide in here got a little mistake. So you follow your books. The books I should be corrected already. So just now, when we say the pure vapor pressure of A and B, the vapor pressure of A at 0.5 is 50. Vapor pressure of B at 0.5 is 75. So total pressure is 125, isn't it? Okay. So we move these informations and we try to calculate the vapor pressure of A and B. So the vapor pressure of A and B, the mole fraction of vapor A and vapor B are shown in here. Excuse me for a while, sorry, I'm going to correct this one because this is wrong already. I've already corrected in your notes, so should be no problem. Oh, I haven't correct, alamak. Yeah, so bad of me. Okay. Okay, sorry, I'm going to correct the notes from here, okay? Pardon me for this very serious mistake. Very careless. Sorry, take out your little time. Okay, so I've corrected for you. Sorry, take your little time. Okay, so now under vapor pressure of A and B, we are going to use the Dalton's Law, which is the third formula, where X vapor of A is equals to PA over P total. So now, we continue from just now. Just now we have already calculated, based on here, we say is that vapor pressure of A is 50, vapor pressure of B is 75 kilopascal. So the total pressure of PA and PB in here are 50 plus 75, which is 125. So now we move these informations to calculate the mole fraction in terms of gas. So in terms of gas, so we say is that vapor pressure of A is 50, isn't it? 50 over the P total, which is 125, you get 0.4. And then XV, you get 75 over 125, you get 0.6. Okay? So we use the same information to build this table. So these tables that I'm going to show you in here are the tables after you calculate by using step 1, step 2, and also step 3. So the informations that you can see in here are the results of after I already recalculated everything for XA and XB using the formula. Okay. So in another word, you have 3 different stages in here. So what are the 3 different stages in here? I mean, this one is the first step where you use the Raoult's law. Okay, where in here you can see that our formula in here is PA is equals to XA times P total. PA not, sorry. Okay, PA not, sorry, this one because of the very limited usage. Okay, where XA is equals to PA is equals to XA times PA naught. Okay, this one you use the this Raoult's law, whereas PB in here you use equals to XB times PB naught in here. Okay, so this is individual by step A and step B. Then you have the second formula where in here I highlighted in terms of green boxes. Okay, where P total equals to P total equal over P total is equals to XA plus XB lah in here lah. Okay, okay. So this is the second step where you have P total equals to PA plus PB. Okay. And last but not least is the final step. So the final step is to calculate the mole fraction of A and mole fraction of B. So is XA equals to PA over P total. XA in here is in terms of gas. Okay, is equals to PA over P total in here. Okay, so now we recalculate all these informations and then we move this information back to the same graph just now. So what would you expect the graph to get? So this is what you expected the graph after you get all this. So the graph will look like this. Okay, so the blue line in here represents the vapor pressure for liquid composition. Okay, the blue line again I would like to highlight in here. Okay, this red line represents, wow, so big. Okay, this vapor pressure composition in liquid state. Okay, whereas this line in here, this blue line in here represent the vapor pressure composition in gaseous state. So do you see the differences in here? Okay, so in other words, what does it mean in here? It means like this, you know. It means that, let's say, if we had at 130 kilopascal, total pressure. Total pressure now is 130 kilopascal. Okay. Under the same vapor pressure, 130 kilopascal. Okay. You shall have a mole fraction of, I used the one just now, 125, huh? 125, I used the 125 just now. Okay, at 125 kilopascal just now, okay, this is the line, 125 kilopascal. In the liquid composition, okay, in the liquid composition, you shall have 0.5 of mole fraction of A and 0.5 of mole fractions of B. Because don't forget, this graph is a two-way graph, you know. What does it mean by a two-way graph that I try to say in here? The two-way graph that I mentioned in here is, if in here, you move from here to here is the mole fraction of A. Okay, mole fraction of A. Whereas the reverse way in here, I use different color so that you can see clearly. Okay, the reverse way is then showing the vapor pressure of mole fraction of B. In here. Okay, so if let's say A is 0.5, B is 0.5, and then you look carefully at the gaseous states. The gaseous states just now is, we said how many? 0.4 of A, and at the same time, it is also equals to 0.6 of B in here. Okay. So with that, that is how you explain how do we get this curve for liquid and gas. Oh yeah, last but not least, everything above this line is liquid. Everything below this line is gas. Okay, so I guess I'm going to end my lesson for right now because it's already 40 minutes, and sorry for all the inconvenience caused. Okay, so I hope that you'll be able to learn well in here. And I also save this video to put inside our class group for further references. You can also refer this to the YouTube later because I'm going to put it on YouTube also. Okay, so with that, I end our lesson today. So any questions, you can always private